Let's prepare on the shear strength of soil. Shear strength. So shear strength is the main character of the soil to be studied. So it is constituted by these characters, that is the structural resistance due to interlocking of the particles and the frictional resistance and cohesion. So these three properties only will give you the shear strength to the soil. And then the term angle of internal friction is important here. So angle of internal friction is nothing but when soil is disturbed or soil is pulled by a shear stress, no? So at that time the force will be like this and the normal direction will be like this. So the angle between that normal and the resultant of the force, so this will be your resultant. So this angle is only, they call it as the angle of internal friction. And angle of repose is also another important one. That is nothing but when you pour a soil on the any flat place, so you will get the soil like this. So this angle, no, so this only they call it as the angle of repose. So these two are very important for the soil to be studied. So this angle of internal friction is generally or commonly 30 degree for the sand, and for clay, that is a pure clay, it is 0 degree. It can be greater than that also, but generally it is 30 for sand and 0 for clay. And for loose sand it is 25 degree, and for dense sand it is 48 degrees. Okay, so next there are several laws talking about this shear strength. So they have different assumptions and they have the different formulas for the shear strength. So first let us see the Coulomb's law. So here they give it as S is equal to C plus sigma tan alpha. So alpha is nothing but it is 5 only, internal friction. So S is your shear strength, C is the cohesion of the soil, and sigma is the stress of the soil. So here for sand they take it as sigma tan phi alone, that is tan alpha alone, because we know that for sand the cohesion is 0. So they can take it like this. And for clay the angle of friction is 0 degree. We have seen here, no? So tan 0 is 0, so that whole term will be 0. So we'll be having S is equal to C alone. So this is all came out of this Coulomb's law. So next we are going to see some factors that the shear strength depends on. Okay, so first one is the past history of the soil, that is OCC, NCC and UCC. So we have already studied this in the consolidation chapter. That is over consolidated clay, normally consolidated clay and under consolidated clay. So when the soil is consolidated in the past years itself, which is more value, that is more stress before, means it is called as over consolidated, but it is more consolidated now, that is the pressure is more on that soil now at the present, means it is under consolidated, and normally consolidated means it is equal at the both the stages. And then the drainage condition of the soil. So here when the soil is undrained, the phi value decreases and cohesion increases, and when it is drained means the phi increases and cohesion decreases. The third one is the saturation condition of the soil. So here the phi value always decreases due to saturation. So when it is partially saturated or dry means it is greater than 0 degree, but when it is fully completely saturated it is always equal to 0 degree. And then the type of soil. So here for sand we already saw that C is equal to 0 and phi will be 30 degree, no? So here they have given us it's greater than 0 degree, and for clay the C will be always greater than 0 only, it cannot be equal to 0, and phi, it is not compulsory that it should be 0 all the time, it can be 0 and also it can be greater than 0 degrees. And then the second theory, so first we saw the Coulomb's theory, no? So now it is Mohr's theory. So here they have drawn this Mohr circle for the soil. So there is always a minor stress and the major stress for the soil. So here sigma 3 will be your minor stress and sigma 1 will be your major stress. And this plane, no, so it will be always having a cohesion here, so which is in the direction of the strength. So as we saw that in the Coulomb's theory, no, S is equal to C plus tan alpha, sigma tan alpha, no? So here the C can be there and cannot be there also, it is based on the type of the soil. So this is a general diagram given here. Okay, so in the x-axis it is stress and in the y-axis it is the strength of the soil, shear strength of the soil. So here what they are coming to tell in the Mohr's theory is sigma 3 is the minor stress, and it can be also called as the intermediate stress also. and it does not have any influence on the strength of the materials. Okay, so that means that the sigma 3, no, it does not depends on any properties of the, that is the physical properties of the soil. And then they tell that the shear strength is always a function of the major principal stress, and it can be never a function of the minor principal stress. And the next theory is the Mohr-Coulomb equation, that is the combination of both. So here they have given us S is equal to C dash plus sigma dash tan phi dash. So here the dash, it means that it is the effective. So it's effective cohesion, effective stress, and the effective angle. So here effective stress means itself it is the Terzaghi's theory only. Okay, so this Mohr-Coulomb's equation is completely based on the Terzaghi's theory. And here the effective stress, cohesion, and angle of shearing resistance is used, and the shear stress at the failure will be always less than the maximum shear stress. So it always fails under, that is below the maximum shear stress only. And the critical shear plane they have given. So at what plane the failure actually happens, no? So that we will call it as the critical shear plane, and the angle for that failure also is given here as alpha f. So at what angle this failure happens? So it is generally 45 degree plus 5 by 2 with reference to the major principal stress, and 45 degree minus 5 by 2 with reference to the minor principal stress. So for clay we know that phi is equal to 0. So whatever may be the reference to the principal stress, the alpha f will be always 45 degree only. So this may be asked in the objective questions. The next is based on the drainage conditions, how the shear strength can be found out. Okay, so there are three conditions of drainage here. So the first one is the unconsolidated undrained test. So normally the shear strength process, no, so we are finding the soil's shear strength, no, so it will be having two stages. The one is the shear stage and the other is the consolidation stage. So first consolidation stage takes place, and after that only this shear stage takes place. So here the no drainage is permitted in both the stages in this method. So it takes just 5 to 10 minutes for the test to do, and it is applicable for the short term stability analysis and dams during construction. So in this all three conditions you should be clear that for what purpose, that is the application of this test has to be known well, because this only they will be asked in the objective. And the quick test, that is the time taken for this three tests, no, so that also you should be clear of. So among these three, so this is the quick test, and the application is, it is used for the dams during construction. And the next is consolidated undrained test. So here the drainage is allowed in primary consolidation stage only, and in the shear stage it is not allowed. Okay, so here what happens means the consolidation takes nearly 24 hours and shearing takes place nearly 2 hours. And the application here is, it is used in the sudden drawdown cases. Sudden drawdown cases means it is nothing but when the dam's water or some reservoir's water is released suddenly, no, so after that what happens to your shear strength. So that condition can be found out using this method. Then the third one is the consolidated drain test. It takes nearly 5 days, and generally they will be taking 5 to 7 days. So 2 to 5 days or 5 to 7 days, both can be the answer. So if any one is given in the option means you can write that. And drainage is allowed in both the cases, that is consolidation and the shear stage also. So here the application is for cohesion less soils and soils having high permeability. Obviously cohesion less only will be having the high permeability, and the long term stability of the clays can be studied using this method, as the time taken is very long for this method. So next we are going to see some test, that is the laboratory test using the instruments we are using for finding the shear strength. Okay, so there are 4 methods like this to find the shear strength. The first one is the unconfined compression test, and you will be knowing it like UCC test. So you will be doing in the laboratories. It will be a apparatus where we will be fixing the soil sample and the gauges will be there. So we will be finding the values with respect to the loads. No, so this is only the UCC. So this test is the one dimension test, and this is an important point, and this is used only for clays that is saturated but not fissured clays. It is not used for fissured clays. So here the main assumption or the main point to be noted is sigma 3, that is the minor principal stress, is taken as 0 here, and the phi, that is the angle of internal friction, so it is also taken as 0 because it is used only for clays. And then the phi, that is the alpha, that is the angle of failure plane, so there they have taken as 45 degree plus 5 by 2 because it does not depend on the minor principal and depends on the major principal stress only. So that only they have taken 45 degree plus 5 by 2. Otherwise you should take minus 5 by 2. So as phi is 0 here, so alpha will be 45 degree and S is equal to C plus sigma tan phi. So this is, they have referred with the Coulomb's law. So that you will get the whole term, this whole term will become 0 due to phi is equal to 0, tan phi is equal to 0. So you will get S is equal to C alone, and this is also the same for clay, we have already studied. And sigma 1 is taken as, that is the major principal stress is taken as 2C tan 45 degree plus 5 by 2. Okay, so here 5 by 2 is, phi is 0, so you will get tan 45 and tan 45 is 1. So you will get 2C as the answer. So sigma 1 is equal to 2C, which means the cohesion is equal to half the major principal stress. So that is only they have given here sigma 1 by 2. So using this method we can also find the effective area of the soils. So here they have used this formula, volume and length of that. So it is V by L minus del L, and also using area by 1 minus, that is the strain. So strain is nothing but it is del L by L. The second test is the direct shear test. So this direct shear test also you will be doing in the laboratory. So it will be like a horizontal plate will be there. You will be filling the soil in that, and the loads will be applied in the horizontal direction, so that you will be adding the weights to the bottom and you will be getting the dial gauge readings. So this is mainly used for the sand types only. So clay cannot be used in this method. Okay. So here this is a two-dimensional test. And the soil specimen size, I told you, the box like structure will be there, so that will be 60 cross 60 with a height of 25 mm. And with respect to this we can find the shear strength. And the diagrams of this stress and strength is given here. So I've already told some soil will be having cohesion alone and some soil will be having zero cohesion. So the sand has zero cohesion, so the diagram will be like this only. It starts from the bottom end, but the clay has cohesion only, so it is like this. It will be a straight line. But in a C5 soil, that is the mixed combination of the sand and clay, you will be having both C and phi. So your structure of this stress and strength will be like this. So here the orientation of the failure plane is fixed horizontal. So in the test apparatus also we will be applying the forces, or the movement of that box will be in a horizontal only, so it is fixed. So this is the assumption of this method, and the measurement of pore pressure is not possible here, so there is no way to deal with the pore pressure in this method, and the shear distribution is complex in this method. The next one is the triaxial compression test. So here it is a three-dimensional test, and this apparatus will be looking similar to the UCC test only, because we will be using that dial gauge apparatus only. And the height of the sample taken here is 2 to 2.5 into d of the sample, that is the diameter of the sample. And here the sigma 3 is considered as the cell pressure. So you will be defining that as a cell pressure, and it can be also called as confining pressure. And another pressure, that is stress, we are taking here is the deviator stress, that is nothing but the difference between the major principal stress and the minor principal stress. So here the formula for the major principal stress is given as sigma 1 is equal to sigma 3 tan square alpha f plus 2c tan alpha f, and the flow value is given as n phi is equal to tan square alpha, where alpha is equal to 45 plus 5 by 2. So here the stress distribution is uniform. And then the pore water can be measured here. Okay, so because this deals with the pore water, it can be measured in this method, and I'll be telling that procedure also in the following classes. And then the volumetric changes are measured here. So the area at failure they have given us A is equal to V1 plus or minus del V by L1 minus del L. And E, elasticity modulus of the soil, can be found out by axial stress by axial strain, that is sigma D, deviator stress by dl by L, where sigma D is also said before, no, so it is the difference between the major principal stress and minor principal stress. The last fourth method is the vane shear test. So this is a very quick test, and most of you won't be doing this test in the laboratories because it can be used both in the laboratory and in the field test. So this is a very important point, because out of these 4 tests, only this can be used directly in the field and lab also. Other 3 can be used only in the laboratories. So this is used only for the soft clays, but actually what they'll be doing in this vane shear test means a rod will be we'll be having a rod, and we'll be inserting that rod into the soil, and a torqueometer will be present on the top of the soil. So the how much torque is required to make a failure in the soil, so that is only measured, and this torque can be converted to the equivalent shear strength. So this is the method they are using, so it can be directly measured in the field. So the torque value is only important here. So when you see that when the both ends take part in shearing, the torque will be pi d square cu, c is nothing but quotient, into h by 2 plus t by 6, that is the height and the diameter of the samples or the soil hole will be drilling, no, so that, and then when only one bottom end part takes in shearing, it is pi d square cu into h by 2 plus d by 12. So this is used to determine the undrained shear strength of the clay. And then comes the sensitivity. So sensitivity is nothing but the weakening of the soil due to the remolding. So it is the ratio of the stress undisturbed of the soil and the stress at the remolded soil. So here the value range is very important. So this they'll be asking the objective questions. 1 to 4 it is normal, 4 to 8 sensitivity, 8 to 15 extra sensitivity, and greater than 15 it is a quick soil. For partially saturated soil, the sensitivity will be always less than 1 only. So I told you know the Skempton's pore water method. So this is nothing but the method to find the pore water from the soil. So we'll be seeing that now. So based on the Pascal's law only this is taken. So here what are the terms they are considering is only 2 terms, that is nothing but the change in the effective stress or change in the stress of the soil and the change in the pore pressure of the soil. So here both these will be in an increasing manner only. So that only they have given us del sigma 3, no? So it is change in the or increase in the stress of the soil and increase in the pore water of the soil, pore pressure of the soil. Okay. So the first one we are going to find is the del mu 3. So it is equal to B into del sigma 3. So here B depends on the saturation condition of the soil and the range is 0 to 1. And for dry soil we take B is equal to 0. For fully saturated soil B is equal to 1. And partially saturated soil it is less than 1. And the second term we are going to find is del mu D. So this is the increase in the deviator pore pressure. So here it is A into B into del sigma D. B we have already seen, no? So here A is nothing but it depends on the type and history of the soil. So when it is a general soil means A will be positive from the range of 0.5 to 1.75, and it is a over consolidated clay means it is a negative from 0 to minus 0.5, and if it is a loose soil means A will be having a value greater than 1. So the total pore water pressure is the summation of these two, that is del mu 3 plus del u3 plus del ud. So it is B del, they have expanded here again and they have taken the B as common here, that is all given here. So the definition of these is given here, I told you, no? So mu 3 is the increase in pore water pressure, and del sigma 3 is the increase in cell pressure, and del ud is the increase in pore water pressure, and del sigma D is the increase in the deviator stress. And then comes the liquefaction. So this liquefaction we already know that when the pore water pressure becomes equal to the effective stress or stress, the effective stress will become 0. So at that time the soil will become like a sand, quicksand condition, aqueous, and the liquefaction is that only. So here the loss of shear strength, because as the stress is equal to 0, no, so we'll be getting a shear strength equal to 0 at that point. So they have told us here loss of shear strength of the soil, and this occurs when E is greater than the E critical. E is nothing but the void ratio. So when the general void ratio of the soil is greater than the critical void ratio, means this condition occurs, and the sigma dash decreases as mu increases. This only I told here. So sigma dash is equal to sigma minus u. So when this increases, this whole term will become 0. So let us see something about the critical void ratio here. So the void ratio on which the volume of the soil doesn't change. So that only we call it as the critical void ratio. So here they have taken the stress and strain here. So how the clays differ with the stress and strain curve. For sensitive clays, it will be a maximum peak of stress, insensitive clay, and then the remolded clay. And the type of failure for the sand is given here. For dense sand, the failure will be always brittle, and loose sand, the failure will be always plastic. Thank you, and keep watching for the next lecture on earth pressure of soil.